some new. So the plan, maybe if you thought it was saying you can go into a something like that. And the plan for the talk is that I start by stating two theorems which won't appear to you at all if you haven't heard about Brauer groups. Then I'll talk about Moduli spaces because that should be the main point here. And these are the main tools to actually prove these results. Then and then I'll talk about the Brauer group. So then some of the things in the theorems to make more sense. And then I'll talk about the applications to these Moduli spaces. And there are actually two things, as you will see in the two theorems. One is about splitting Brauer classes, and the other one is about the so-called index theorem. Okay, so let me into it. So splitting Brauer classes. And the next problem. So let's start with a smooth projective variety over a variety closed field. And then the first theorem says there exists an abelian variety over the function field of x. So we access the function field. So then there exists an abelian variety over the function field such that for every Brauer class, for every element in the Brauer group of x, there exists a tensor the alpha that splits alpha. So that means if I restrict the Brauer class on x, that's given on x, to Brauer class over the function field. So the abelian variety was defined over the function field, and then the torus was also defined over the function field. So I can pull it back from there. And this maps the Brauer class alpha to the trivial element in this group. And the way to think of this abelian variety, more in metric terms, so this A over kx, just think of this as a family of abelian varieties over x. The generic variety is really abelian variety. But in the end, it's all about the generic variety. So this is the first theorem, and the second theorem is the second theorem is they exist in number, but only depends on multiplying the x, such that for all alpha in the Brauer group, the period of alpha, the index of alpha divides the period of the alpha to the power n. Okay. So the second theorem, this proves the conjecture. The conjecture of De Jong and Perry, or maybe a year or 2 years ago, and they proved this theorem assuming one of the standard Lefschetz conjectures. They proved this. Assuming the Lefschetz conjecture. in degree 2. There's a more general conjecture that actually determines the M. I'll mention this maybe later. So I think you would agree, if you haven't seen it thought at all about the Brauer group, these two theorems won't speak to you at all. Okay. So I'll go into Moduli space of system G to motivate why it's interesting to look at these Brauer groups, and I actually find the Brauer group for you, and then some of these two theorems will become okay. I don't despair yet. Okay. So this brings me to second point. Moduli space of this please. So there are various ways of thinking about twisted trees. The main for me are three, and I mentioned all three of them, but there are actually more. So there's these three. Thinking about those. And they have different advantages and disadvantages. Okay, so the first thing, and maybe so there's a theory that works for projective varieties, but my main interest is actually in curves. So it simplifies a couple of things. So for instance, you may assume smooth projected over some period K. So when I write capital K, I want you to think of the function, so big theory. Not necessarily everybody knows, or projected rightly projected. And the first point of view starts with algebras. So let A be not some algebra. What is not some algebra? Eta locally, A looks like that. Matrix algebra. Matrix algebra. Maybe let me write down here in red an example. So A, for instance, could be an amorphism algebra of a local species. That would be one example. Of course, so that would even the risk locally be of this form. In general, you assume eta locally. If you work over complex numbers, then you can also work with the analytic. Okay. And then you can look at the unique category of coherent A modules. A modules. So for instance, in this example of locally, where A is the most module of locally species, this is the unique category. This is equivalent to the usual unique category of coherent sheaves, and this equivalence is given by taking E, by taking a locally species E here and mapping it to F. And so E, and then you see this becomes the A module. And it turns out that this is an equivalence of categories. So in this example, so usually that's my algebra is not of this form, but when it is, this repeating category is just the standard thing. Okay, and then there is by Simpson. It's in one of his very first papers, early 90s, late 80s maybe, and then in positive characteristic. Then it's a paper by Hoffman that says there exists a Moduli space of stable A modules. Moduli space. Stable A modules. So I assume you all know how to define stability of sheaves, so let's say vector bundles. Then so you compare the slope of subsheaves. So you say the slope, something is stable, the slope of any subsheaf is smaller than the slope of the sheaf. And here you do the same thing, but you only look at a submodules. Okay, so that's and then if you want to fix, you want to get projected for one projected model space, then you have to fix some numerical invariance. So it's the invariance. Get M-A-R-D. So these will be A stable A modules. The rank of that would be R, and the degree of that would be D. And one finds that the R is always divisible by can always be written as R0 times for the degree of A. The degree of A is nothing but the rank of A and the square root of it. You see, locally the rank of A is always the square, so it's n squared, so I can always take the root, and any if it, assuming the rank is positive, any A module will have a rank that's a multiple of this degree. No. So the special case would be the case where this R0 is 1. Special case. So we take B A C, and that will be M A. So that's not a minimal value for the rank, and that's why, as for untwisted world, in the control space of bundles, the smallest one is the first case is the Pythagorean. That would be the twisted Pythagorean. Again, in the example, when A is a dimorphic sheaf of locally free sheaf, of course, the twisted Picard is isomorphic to some component of the Picard variety. And then there's that's maybe not so interesting, but anyway, degree minus degree of F divided by degree of the atom. Okay, so in this case, we don't create any new varieties. It's just the good old Picard varieties, maybe indexed. Maybe I can add one thing. Whenever I have an A module, a stable A module, I can twist it by line bundle. It stays by an ordinary line bundle. It stays a stable A module, and that makes these things here false, so we pick 0. We pick A C R 0. Okay, so that's one way to think about twisted sheaves. So these are just models over Natsmaya. So the second way of thinking about this, which comes closer to the name, is we give ourselves a core cycle. Is now locally, and we look at the revealing value of twisted sheaves. Yeah. G. Curly G consists of coherent sheaves on each of its open subsets. And then we have joinings on the intersections. And those gluings satisfy a certain condition, namely, so the usual core cycle condition would be that the composition finite J, finite K, finite K, is the identity, and here we put instead alpha J K times the identity. Now this is again an abelian category of twisted sheaves. And again, in this language, you can define Moduli spaces, and this comes, it's not quite the language Liebig uses, but this comes very close to early work of Liebig, showing again that there is a Moduli space of stable twisted sheaves. And of course, much more than just Moduli space. Stable alpha twisted sheaves. If you fix numerical invariance, then you get it in quasi-protected Moduli spaces. But fixing the invariance is it's a little, has to be a little careful. It's not clear how to define numerical invariance or stable. And again, for our special case would be take the alpha, that would be the case of rank 1 space of rank 1 sheets, another space of alpha twisted line models. Okay. So there is a way to go between 1 and 2. That goes as follows. Link 1 and 2. Maybe if I take a locally free sheaf, twisted sheaf, locally free, then I can find an axiomal algebra that looks as before, but has isomorphism algebra of a twisted sheaf. But that's again axiomal. And then this category here becomes the abelian category of A modules over C modules, and what's the map? So I take E and map it to GQ in the E. And you see, so since E is a twisted sheaf and G is a twisted sheaf, so G dual will be twisted with respect to the inverse of alpha. This becomes an untwisted sheaf, and at the same time it's an aging model. So these are just different languages of describing the same category. Note the Moduli spaces correspond to each other, but then comparing the invariance is a little tricky because it depends on the choice of this G here. Change the choice of the G. For instance, by twisting with the line bundle, the axiomal algebra will not change the invariance rule, so it's all a little technical. Okay. So that was this comparison. And the last one, the last way of thinking.
So, going back, can you recover alpha or only its class?
I cannot. No, I cannot. I cannot find the cycle itself, and that also causes a problem. Later, someone will talk about homology classes when I look at those things as elements in the Brauer group. The categories will depend on the Brauer class, but not canonically, which is a headache. Okay, and the last way of thinking about is in terms of Brauer severe varieties. Varieties. So eta locally. These things look like there's the projected bundle Pn over U, and the example, the trivial example is that I start this before with a vector bundle and locally free, and I get Brauer's variety. That's projected by Z F, but in general, Brauer's varieties are not projectization of locally species. And once again, you can write on the abelian category. P of X. And these are coherent sheets on the browser grid, right? Upstairs, plus the additional condition that that the junction map the natural junction map is an isomorphism, so you single out certain coherent sheets on P plus this additional that satisfies this additional condition. And what is this omega P? This comes from the relative Euler sequence, which you definitely know for the projectivization of a locally free sheet, but which also exists for Brauer varieties. And there's a unique extension, distinguished extension of this form. And this sometimes people call this the Grünband because one of the papers it makes appearance already. And that's the condition. And again, there's a moduli space theory for it, and this goes now back to Yoshioka. Yoshioka, there exists a moduli space of stable sheaves. Moduli space. So moduli space of objects in this memory, moduli space of objects. In the space. So Simpson's moduli space construction was the first, and then somehow independently reconstructed these moduli spaces.
It's sometimes
And there's a way again of linking 3 with the other 2. So for instance, if I want to maybe 1 by 3, then so I start with the Brauer variety, we C over X, and then I it's the projection, and then I get an anti-mile algebra by taking the direct image of the endomorphism of this Quillen bundle, and I can also link 2 and 3 by saying if I have a twisted sheaf alpha locally free, then I can projectivize. And since in the definition of a twisted sheaf, I do have the cosine condition up to the scaling, but the scaling, this multiplication with the alpha ijk, for the projected bundle, they don't matter. And so those actually glue to a Brauer variety over. Okay. So first remark is
that that's a projected bundle, right?
That depends what you mean by projected bundle.
It's not very clear. You can speak, but not very clear.
No, this is okay. My blue in there, they are eta. So this is only eta location. So if you have a Brauer variety that over Zariski open set looks like Pn times something, it is actually trivial. Right there, approximately right there.
We are saying here in section 3. What are your objects? Are those parts, browser, variety, classifier, model?
So this is the full subcategory of all functions on P satisfying this condition. That's all. That's a full subcategory.
So if you start with the G involves the alt, then you produce P and the coherent sheet on P, right?
Now, first of all, I just take a look at the sheet that we use about the variety as before. When I compared 1 and 2, I start with a local sheet and produce an Maya.
Modules of the because they respond to this.
Yes. Okay. So the first remark is if C is a curve, overnight right closed here, so capital K is underlying closed, then my result what was that by then? Every Maya algebra is of this one. Is. But that means we don't gain anything by looking at a smile as the curves overnight by the closed field. We are immediately all equal to category we know already, one is with no equal isomodules we know. Okay. If C is defined over non-algebraic closed field, then my varieties are new varieties, new Moduli spaces, new electricity varieties. They become after passing the algebraic closures, taking base into the algebraic closure came up, become the old Moduli spaces. That means what we define are just forms of the classical Moduli space itself. Forms of the Moduli spaces. I.e. after phase change to the K bar, we get effect what over curve one typically calls the varieties or those Moduli spaces of stable rank R bundles of the BD. Okay. So now the question is why are we doing this? Especially for someone like me interested in complex algebraic varieties. Why not just taking C here and then I don't gain anything new? So question is why getting into this? And the point is if consume access there's multi-vector variety. Variety knows here. So for instance, C. So more specifically, this would be F would be X would be KT, so it's F for the complex numbers. Then there do exist algebraic that are not of this form, that are not homomorphisms of F. Then exists the A's which are not homomorphisms, and P's also varieties which are not not of course not for every smooth projected variety, but for instance for KP surface. And then, for instance, if X is KP surface, we can look at Moduli spaces. So before I only dealt with the case of curves, but now I'm doing the same for the KP surface. So if X is a KP surface, for instance, over C, then I get Moduli spaces and a V, so that would be Moduli space of stable A modules. And with a given movement vector, if you don't know what a movement vector is, just fix the turn classes, fix turn classes. And typically, if the vector is chosen nicely, so typically these things are smooth projected varieties, deformation equivalent to Hilbert trees. So it's like in the untwisted case, if A is just a structure sheaf, I get my moduli space of stable sheaf on K3 surface, and the Mac vector is primitive as a relation, shows generically, then I get just the information of the sheaf. Okay, so now I'm interested in a special case where the Mugler vector is such that all the sheaves are concentrated on curves. So let's look at a special case. The rank is 0, and there's a third term class, if you want to do H, and then there's a second term class C2, and then a point in moduli space from stable A modules with this Mugler vector corresponds to the put forward of the sheaf. The G is an AC module. So I can restrict the given Atomai algebra. So when I say Atomai algebra, I could as well think of twisted sheaves or E from the Brauer variety that we stick to Atomai algebra. So I restrict my Atomai algebra to C. If it was an Atomai algebra on X, it will be an Atomai algebra on C. Locally, it still looks like matrix algebra. And then I look at modules on C, stable modules, and the E is actually the push forward of a sheaf on this curve, on this curve C. So in the untwisted case, I could do the following. Case I could look at the complete linear system, and the complete linear system H, C over H, and then look at the relative Jacobian or relative pr of this family over the system. And that would be an open subset of my Moduli space of stable sheaves. Here I put OX, so here it's my algorithm trivial, H C2. And the D and C2, they correspond to each other, so that would be an open subset. So my Moduli space of stable sheaves would be natural compactification of the relative pr of the universal curve. And the fibers here are, of course, closed by this isomorphic brightness for the linear system. Okay. In the twisted case, so I start again with my family of curves, but now I don't look at line bundles of C, but I look at line bundles there are A modules. So I get D, C, and this is my algebra over H, which will be compacted by my new Moduli space. Okay, and again, the fibers are now these twisted Picard are introduced where restrict A, get the atomized over each curve by restricting atomized over A next to C. And now, if I start with a variety over a variety closed field like C, then and I take a closed point in the system, then this is the curve defined over C. So these two things they are actually isomorphic. So the fibers of these two families are the same. Okay? But so same fibers, but they are sort of put together in different ways, but non-isomorphic families, in general, of course, and isomorphic families. And the best way to see this is to look at the generic point. So if I take the generic point here, so the generic fibers the variety of the AD line bubbles on the generic fiber. And this is in the untwisted case, and in the twisted case, it is the twisted Picard variety. And now the C eta now is a curve over non-algebraic closed field. And these two varieties, there's no reason why they should be isomorphic. So you can see that these two families are globally non-isomorphic because simply the generic fibers are just not the same. Yes, and maybe I space for good theory. So there's a major input by Markman, and then we use our language to rephrase this as follows. If you have a hyperkernel and also the text, that's for those of you who know the hyperkernel of KTN type. So hyperkernel that have information of delivery schemes plus you give yourself a vibration over Pn, which automatically is a Lagrangian vibration. So every Lagrangian vibration of a hyperkernel of KTN type is actually of this form. Then X is birational to some twisted thing for some KP surface S and H. So you start with any hyperkernel. The only thing you assume is that's a deformation to a KP surface. And Markman shows there is always, in this case, there's always some KP surface around, and then reinterpreting this result, we can actually say then X is birational, one of those twisted Picard schemes, or one a Moduli space of twisted sheets on the GPs. So that explains the Lagrangian vibration for one of the two standard series of film. Okay. So now I should come to our Brauer roots.
Did you see what A is here?
That exists.
Okay.
So that's the I mean, first of all, not unique. The A is never unique. It's only the Brauer class is unique, but that not much like two. So in this paper, I didn't want to go into this. In this paper, we developed so we're using road nodes by Goethe, the special Brauer group, and that's actually the national object to look at. And then some of this class and the special Brauer group would be we need to determine by the original Lagrangian vibration.
So if you in this theorem you have this birational, right?
Yes.
So how much control you have over?
Well, I mean, there could be the experts have different birational modules. So yes, so you could have different birational modules of the hyperclear, all given, all coming with a Lagrange information of the same Pn. Because you could have a Pn in one of the fibers, and then you can move by flop this Pn, and then you get still hyperclear manifolds, which still have Lagrange vibration over the same Pn. I mean, you could hope that if you assume that the vibration is really a regular Lagrange vibration, really defined everywhere, with the minimum models you need, then it will be given by this model space. But that's not quite true because of this. Okay, so now I think time is should tell you something about the Brauer group. Let's say, if I'm more generally, but that's assume X is right over K, then there's a chronological definition of the Brauer group, which is just in terms of data homology. So for K equals C, there's a close link to the second the wave two structure of X. Wave two structure. And in a way, this is why I get interested in the Brauer, because I'm interested in wave two structures. And there's a different interpretation of this in terms of Atsumaya algebras or Brauer severe varieties. So let's say this is the group Atsumaya algebras module certain equivalence relation, and or you could say this is instead of Brauer severe varieties. Module certain equivalence relation, and this here is the proper theorem. So this is how to spectrum cover, and then you go and control it, extend it, and so on. Okay. So here we explain the Brauer group in terms of two of the different ways. Here's Atsumaya, and here's the Brauer variety. But we know we also can think of if you come from here and think of this in the analytic setting, and this will be H2O star. Try to use check homology to represent class again. So alpha is alpha ij k. Then an alpha and the G is an alpha twisted bundle. Then, as I told you, we can define this Brauer class, the Brauer variety over X as just as the projectization of this thing. And maybe one remark is, if you find a sheaf of rank 1, globally free sheaf of rank 1 that's alpha twisted, then if you projectivize it, then you just get X itself. If you project something of rank 1, of course you get just X. That means you get a Brauer variety of it's just X, and that's the identity in this group. So if rank of is 1, then the Brauer class it's just the unit in the Brauer group, and more generally the order of alpha always divides the rank of G. Okay. So now there was one page of history which I will skip. Maybe I just say. So there are two parts in the history. It all started in the pure algebraic setting 100 years ago. So X is state K. Then we started the Brauer group of K. And this is, you just view it as a set of isomorphs in classes of division algebras over K. Over K. Or the equivalence classes of central simple algebras. The algebras module a certain equivalence relation. And And then just a bit of notation, the period of the class alpha is nothing but the order of alpha. And the index of alpha is the minimal, is the dimension of D, and I'm just going to the dimension of D, then it's Huybrechts. Within alpha, and can also be computed as the minimal degree of a finite extension of K that is split alpha. So if you have a division alpha, then you can twist it by L, and if this is matrix alpha, then the L split, say L splits alpha. And the general fact is that the period always, with the order of the class alpha, always divides the index. And moreover, these two are the same prime factors. So that means the index of alpha divides some power of the period of alpha. And so this is the algebraic situation. There's a beautiful book by Julie and Samueli. And for the algebraic theory goes back to Bonn, the early 60s. There are three Bogerty talks, and then they are reprinted in this volume, these exposés sur la chronologie. And also give my recommendation is this great book by Goethe University Frankfurt. But you also find this done by another. The important thing is there's a link between the two by the function field. So if x is true or locally factorial enough, then restricting, so if you have an atomar algebra over the scheme, you can restrict it to the generic point that gives the element in the Brauer group of the function field, and that this one is always neglected. So the Brauer group, you don't lose any information by passing from X to the Brauer group of its function field, but this group here is much bigger. And also, so when you put it, if you think, well, maybe if I pass a different birational module of X, then I take different classes of the function field, but that's not true. So the Brauer group is the birational invariant of the right. So I'm afraid this is all I want to say about the Brauer group. Now talk about splitting Brauer classes. So I mentioned the algebraic system already. There's this thing about the computing the index by looking for a finite extension that split the Brauer class, splitting fields of the Brauer class. And if in the geometric setting where the capital K is the function field of the already, the finite extension of the function field, of course, corresponds to a finite coloring of the writing, and that means it's a Brauer class, and it's a finite morphism such that I have a style of generic defined what we think of like cyclic covering of the surface. Typically, you don't lose any information for when you look at the hot structure, the Huybrechts will be injected, but that's not quite true for the Brauer group, although it's determined by the hot structure. So for every Brauer class, there is a finite extension, finite covering that splits the Brauer class. So this is finite extension, but you could also finite morphism, but you could also ask for morphisms that are far from finite. So the first example, the second example is so a Brauer class corresponds to a Brauer severity. Then the pullback of the class alpha is also trivial. So that's an element of the Brauer group of the writing upstairs. In fact, the kernel of the pullback at Brauer X to Brauer P is generated by this class. Alpha. So it's not an untypical thing that you find a variety as innocent as the Brauer severe variety that splits the Brauer class out. So we pull back the Azumaria algebra, all of a sudden it's the endomorphism of locally Fishy. And then there's a question which actually goes back to Roquette. So one of the main theorems in the algebraic situation is a theorem of Brauer-Hassen-Noether about every central algebra being is cyclic algebra, and the student of Hasse was Roquette, and he looked at the following question in the case of local fields, but more recently it was really placed like this by Kraut and Thorman. If every Brauer class can be split by genus one curve. So the question is so let's exit generically genus one curve. So then you can think of genus one curve over the function field. Genus one curve. Such that the pullback of alpha is trivial in this unit. The genus one curve cannot be an elliptic curve because it's an elliptic curve. The pullback of Brauer can never be true. It can only be genus one curve. Okay, and this is okay by results of 4 de Jong. And then well, I'm sure the earlier work by Huybrechts. That's okay if the index, so what you think of the order of alpha is smaller than 6, and some partial results for order 7. I think in general, we do not expect this to be true in general, but it's an interesting question. You could even ask for more, maybe whether you can like say something about the J index of the curves with mountains.
So X is the most general setting here.
Right, here X could be set in. Okay. So I have 5 minutes left, but better come back to this the original yeah, so maybe one reminder before I do this, if I have a curve, it's an over function field, and I pull back the class out, so within, I should say, and such that the pullback of alpha is trivial, then the periods of the order of alpha divides 2g of the curve minus 2. So you see, instead of elliptic, you could ask why elliptic curves, why not one bundles of X or curves of higher genus? But then you can expect a uniform answer because the order for all ground classes, because the order of alpha will always divide this thing. So when the order grows, then the genus has to grow, except when the genus is 1. Okay? Then in principle it's possible that every Brauer class is split by curves. So there is a result by Brauer and Lieblich from 21, and they prove the existence of all Brauer classes on X. They exist in the Wien variety, A alpha, Wien variety plus an A alpha torso. So that's the equivalent of an elliptic curve plus a genus 1 curve. Also V alpha that splits such that so all the functions of X such that so restricting to the generic point is injected, then you can pull back from the base field to the Brauer group of the alpha. The number is more this market goes to 1. But this the abelian variety A depends on the class alpha, and moreover, actually, its dimension depends on the class alpha. Dimension the alpha depends on the index of alpha. And our theorem 1 says there exists an A that is independent of alpha, and then you only have to choose the torso over this A to split the Brauer class. It's A independent of alpha, independent of alpha, but the just E alpha splits. Okay. I have 3 minutes to explain to you how the Moduli states come in.
You have a question, why do you the variety?
Well, simply because we can't do it good. Yeah, so as I said, I don't think people generally believe that there always exists ability curve. So real writing is the best thing we can do. But it's very good to let people out for other types of writings that split your writing. But already the case of curves tells you, you have to be careful what you wish for, because the gene tells you wrong. Or something similar will happen in the high dimension. Now the idea is it's very simple. So you take in a way, I think the experts just overlooked some of this construction. So I pick a family of curves. So think of a left extensor for a surface, or roughly a left extensor for surfaces, and then this map is birational. Then I look at the relative power. So that's a relative power of this family of curves. Okay. So this is the Moduli space of sheaves on the fibers of this family of curves, but of twisted sheaves with respect to this the Moduli space of twisted sheaves on the fibers. Okay. And as in an ordinary case for Picard varieties, you hope that there's a pointary bundle, and then we have to work a little bit. So assume there exists a pointary bundle. But now the pointary bundle parameterizes twisted sheaves on C. Okay, so this will be a twisted sheaf, the one alpha twisted sheaf on this product. So the alpha comes here because that's a Moduli space of alpha twisted sheaves. The one here is the condition that they exist, that this Moduli space is a fine Moduli space. And for this, you have to work a little bit. But now you restrict this whole thing to the function field of C, which is the same as the function field of X, and because that's a birational map. And what you get is, if I do this, the alpha of C beta, when I take the generic fiber of B of the data B, a base change to the generic point of C, and do this over the function field of C, which is the function field of X, then I see that this Poincare bundle is a twisted sheaf on this thing, so twisted with respect to the pullback of the class. But the Poincare bundle is a bundle of rank 1 because these are line bundles. So what I found is a twisted line bundle, so alpha twisted bundle of rank 1. And then there's the remark, which is probably hidden behind here, that says whenever you have a locally free sheaf of rank 1 that is twisted, then this twist, this Brauer class has to be trivial. So rank 1 implies the pullback is pullback of alpha. It's trivial. So I'm using this Moduli space of twisted line bundles to split Brauer classes. You could try to use other Moduli spaces, but somehow you always have to work with something geometric, and this is the complete intersection curve. That's the thing that's always there. And so this is the idea from theorem 1. And theorem 2, then we observe we can use the same argument and produce by taking global sections of the Poincare bundle, produce alpha modules of a certain dimension, and that eventually gives you a bound on the index in terms of the theorem. Thank you.